Hello everyone. Let's just talk about the carry look ahead adder. So basically this is an important concept in digital electronics or if I say the combinational circuits. This is very important concept. So for the combinational circuits, let's just learn this thing, how it works, how we implement this, and what is the use of this, and what does it do. So basically this minimizes the operational speed of the computer by making the carry thing independent of each other but dependent on the very first priority thing. Okay, priority thing one. So basically what does I mean by this is, first of all, let's just introduce with the half adders and full adders. Basically we have two types of adder. One is half adder and the other one will be the full adder. Okay, so what does the both do? They both do adds the various terms. Like for the half adder we will have a b as our inputs, so our truth table would be of 2 raised to power 2, it will be 4 bits. Okay, and for the full adder we have when we have a complex circuit, like we have three terms to add, we have a b c, then we will use the full adders, and this will indicate the bits. So we have 2 raised to power 3 will be 8 bits. Okay, so we will have a drift table of 8 bits. So basically the carry look ahead adder works upon the principle of full adder. And how it works on the full adder thing, let's just take, for example, let's just take for the four ones, the full adders. Let's just take the 4 full adders. Okay, so this will be my adder 1, sorry, adder 4. This will be my adder 3. This will be my adder 2. This will be my adder, sorry, let's just start from 0. 0, 1, 2, 3. So this makes it the 4. Okay, so when we have the inputs here, and for the first one we have the inputs, let me just clear this. For the first one we have the inputs A0 and the B0 thing. Okay, and for the second one we will have the inputs A1 and B1. For the third one we have the inputs A2, sorry, and B2. For the fourth one we'll have A3 and B3 because it starts from 0th term. So for the first one, what will the adder do for you? Since we know that the adder will create two things, first one will be the sum and the other one will be the carry. So the sum will goes here. We're gonna ignore this because we are talking about the carry look ahead adder. We're talking about the carry thing, so we're gonna ignore the sum thing. Okay, so the sum for the first time we have a0 b0, sum will be s0. Okay, and the carry will be c1, c0, sorry, c0. And for the second term we have the one term a1 b1. That will means that we have the sum 1 and the carry will be c1, and for the second one will be s2 and c2, followed by the c3 and s3. Okay, so now let's just make some truth tables regarding this so we can verify how this adder works. So basically what is the concept? First of all, let's talk about the concept. We have the c3, c2, c1, and c0 are the carriers, and this is our c input. Okay, so what does the carry look ahead adder do? This will do the thing that it will make the c3 as independent of c2, c2 as independent of c1. This means that this term is not dependent on this carry term. Okay, c1 is not dependent on c0 similarly, but all of these terms are dependent upon this input term. Okay, so we have the c3 directly dependent on the cin, c2 directly dependent on cin, c1 directly dependent on cin. Okay, now this will reduce the operational speed and performs the operations at a faster rate for a computer system. So let's just prove this thing that how the C3 depends upon the Cn term. Okay, let's just prove this thing. So since we know that when we have to prove anything, we're gonna talk about its truth table. So we have the bits, which is 2 raised to power 3, 8 bits. Okay, so we're gonna make the 8 bits truth table. Let's just make it right here. So we have 1, 2, 3, and there will be our carry, there will be our, this will be our output. Okay, this will be our inputs. So we have A, B. So let's just talk about a particular adder circuit. For example, I'm gonna talk about this, the first one, the adder one. Okay, this is the first one, so this is the second one. Let's just talk about the adder one. Okay, the adder one includes the input A1, B1, and C0 as the inputs, and outputs will be S1 and C1. Okay, so let's just write them. AB, A1, B1, and C0 are the inputs. C0 are the inputs, and the output will be C1. Okay, output will be C1. So let's just make the truth table. So I'm gonna write all instances. Let me just write them. So we have 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. Okay, so now just use the carry thing. So by using the basic mathematics, we have 0 plus 0 will be 0, 0 plus 1. Now the carry, it will only generate carry when the adding thing will be greater than 1. It means that if we add the terms and we get the output as greater than 1, then the carry will be generated. Otherwise it will remain 0. Okay, so we have 0, 0 plus 0 plus 0 will be 0, 0 plus 0 plus 1, it is not greater than 1, so we'll have 0. So we have 0 here also, and you can see now 1 plus 1, which is 2, which is greater than 1, so we will generate a carry of 1. 1 plus 0 will be 0, and we have 1 plus 0 plus 1, which is 2 again, so we have a carry. We have a carry here, and we have a carry here as well. Okay, so now, so for equations we have, if we have 1 here and all the instances are 1, then we will rewrite A1, B1, C0 as the same without a bar. Okay, but if we have the 0th term here and the output is 1, so that means that A1 will be written, in this case, for example, it will be written as A1 bar. So let's just make equations. Okay, for the last term, we're gonna see that it is, the output is 1, so the result will be A1, B1, C0. Okay, plus, and remember that this is our C1 equation. Okay, we're gonna make sure that C1 is dependent on the first term. Okay, C0 term, we're gonna prove that. So the first equation will be A1, B1, C0. The second equation will be A1, B1, and C0 bar here. Okay, in this case. Now the third one will be A1, B0, sorry, B1 bar, okay, and C0. Okay, and the fourth one will be this term. Okay, so this means that A1 bar, B1, and C0. A1 bar, B1, and C0. Okay, this is our equation. So for the first term, we're gonna use the mathematical rules or algebraic techniques to solve this equation. Okay, the Boolean equation. So we have C0 and C0 bar. Notice that we have these terms here. So okay, so we're gonna take them common. So we're gonna take A1, B1 as a common thing, and C0 plus C0 bar. Now that will make us make the simplification a lot easier. So we have the plus sign here, followed by A1, notice that this is the A1 B1 bar C0, A1 bar B1 C0. This is the this reminds me of the gate that is XOR gate. Okay, that is XOR gate. So I'm gonna write this term as I'm gonna take C0 common, so I'm gonna write C0 here and B1 A1 bar plus B1 bar A1. Okay, now this reminds me of the gate which is XOR gate, so I'm gonna rewrite it as B1 A1, so this will become 1. Okay, since we know that if we have the opposite of something in Boolean expression, it will make it 1 by simplifying it. Okay, this is the technique. So we have the C0 here, and for the second term we have B1, and this will be the XOR with A1. Okay, now basically this is the main equation of the C1, okay, that we'll be using. So notice that this thing here, this equation has two parts. Okay, the first one and the second one. This thing here will be called as carry generators. Carry generators. And this thing will be called as carry propagators. Carry propagators. Okay? So we have the carry generators and the carry propagators. And we had to prove that the C1 was dependent on C0, and that is directly proved by this equation. Notice that the C1 is directly dependent upon the C0, okay? So, or the concept of carry look ahead was clearly visible here as well. So now the last thing we're gonna do is drawing its block diagram, okay? So for the block diagram, we're gonna make the gates, okay? So we have the XOR gate, we have the XOR gate, okay, and we have the AND gate. We have the AND and XOR gate. We're gonna have to combine this, okay? So for the block diagram, let's just say we have the block diagram here for all of the circuit that we learned, okay, for the 4 adders that we drawn earlier. Okay, so for them we're gonna take all as inputs. So let's just start with the last one adder, which was the 4th adder. Okay, so the terms will be, for the XOR gate, it will be B3 A3 as an inputs, and followed by the AND gate. Okay, and this will give us, now why I'm adding the XOR gate and AND gate in proportion along each other, because we had the equation which consists of the 2 instances. So for the block diagram, we're gonna use the XOR and AND as the B3 and A3 are inputs, and notice that the XOR part was our carry propagators. We're going to represent this by this, and this will be our carry generators, the AND part. Okay, and for similarly we have the second one, which is let me just draw it right here. Okay, this is the XOR, and for the inputs were B2 and A2 in this case. Okay, and they're connected by the AND gate here. So this will be our carry propagators, this will be our carry generator. Okay, and furthermore we have the A1 B1 as well. Okay, we have the XOR gate. Sorry, first of all we will have the XOR gate, and then we will have this input will goes here, and then we will have the AND gate here. Okay, so this will make it as the carry propagator and carry generator. And similarly for the A0th term, but I'm not gonna include that here. So we have the CN term here, the previous input on which all of these inputs are dependent. Okay, all of these results are dependent, so we take this as well. Now all of these carry propagators and generators are connected. Okay, for in a data circuit. Okay, so the term from the, let's say for the A1 and B1 we have the inputs. Okay, these are the inputs. So the result of these will be here. Let's say I will make a gate again. So I will make a gate again. Okay, let me just make it here, and this gate will be our sum gate, which will give us the output, and this will include the P0 or and the Z term. For I'm assuming that this whole circuit output is P0. Okay, now what is the P0 and G term here? Basically, why I'm adding these two terms, this is our the generators, and this was this was our propagator, and this was our generator. And when we combine these two by an XOR term, okay, notice that we have an XOR, we get our sum output. Okay, so this is basically the output that we will get from a circuit. Okay, from a circuit of XOR. Okay, the XOR will accept the two inputs, so we have the C and the first one, and the whole combined output of one circuit will be gone towards an XOR, and that will make it split this up in two parts, which will be propagator and the generators, and both will add to give us the result sum. So this was our basic building block diagram. So this was it for today. I hope you will ignore my mistakes. See ya.